On the ocean floor, just millimeters stand between order and catastrophe. Chinese engineers didn't just build a 5-kilometer undersea tunnel beneath unstable silt and crushing seawater. They rewrote the playbook with technology so precise it rattled American experts. But what secrets did their ground surveys uncover, and what dangers wait beneath the surface? The real story begins where most engineering stops. Survey vessels swept the bay, bristling with multi-beam sonar arrays that mapped the seabed in strips up to 200 meters wide. Every pass produced a digital elevation model, accurate to within 10 centimeters, revealing hidden slopes, boulder fields, and subtle shifts in sediment. Engineers scrutinized the mesh for any sign of instability, a sunken container, a sudden dip, the faint outline of a buried void. But sonar alone could not tell the full story. Teams drilled more than 600 core samples along the proposed alignment, each boring plunging 25 to 80 meters below the surface. In the lab, geologists logged every layer: slick marine clay, loose sand, fractured granite, and pockets of open space as wide as a man's arm. One core flagged a karst cavity at nearly 30 meters depth, coordinates tagged and entered into a digital model. Every data point fed into a building information system, creating a live, centimeter-level alignment grid that guided every design decision to come. Marine biologists and local fishing cooperatives gathered around the conference table as planners unveiled the impact assessment. The tunnel's alignment would cross feeding grounds and disrupt spawning routes, a reality that could not be ignored. Environmental officers outlined strict noise controls for every phase. Hydraulic hammers and underwater drills were limited to specific windows when migratory fish had already passed. To offset lost habitat, project contracts required the installation of artificial reefs. In Dalian Bay, more than 13,200 square meters of concrete modules were lowered to the seabed, staggered before and after tunnel immersion. These reefs, monitored for fish return and water quality, became a lifeline for displaced marine life. Compensation agreements signed with local fishermen guaranteed 11.9 million yen in payouts, funds contingent on meeting ecological benchmarks verified by third-party audits. Every route adjustment and method selection was now shaped by these obligations, forcing engineers to weigh environmental costs as heavily as technical risks. At the fabrication yard, engineers orchestrated the assembly of colossal tunnel segments, each stretching 217 meters and weighing 73,000 tons. Robotic welding arms traced seam lines with a precision of 0.02 millimeters, fusing steel shells and concrete into a composite 4 times stiffer than traditional designs. Tolerance was unforgiving. Every surface and every edge had to land within a margin of 1 to 5 millimeters. Gasket specialists inspected grooves for microscopic flaws, knowing that a single imperfection could compromise the watertight joint. When finished, these segments became the backbone of the tunnel, ready to float out and settle onto the seabed with a fit so exact that even the ocean's relentless pressure could not force its way inside. Deep beneath the bay, the tunnel boring machine roared to life, a 12-meter steel cutter head weighing 200 tons, spinning with relentless force. Its 140 disc cutters bit into the seabed, pulverizing sand, clay, and fractured rock in a single, unstoppable advance. Inside the control cabin, operators monitored every pressure gauge and torque reading, fingers hovering over emergency cutoffs. Foam and water injected at the cutter face formed a pressurized shield holding back the threat of collapse and flooding. The machine pressed forward, assembling 8 to 10 concrete rings each day, but when sensors detected a sudden drop in pressure, the entire system shut down within seconds. Crews scrambled to stabilize the foam mix, recalibrate the balance, and only then did the tunnel boring machine resume its march. Each crisis was a reminder that here, even a moment's hesitation could bring disaster. When the machine stall or geology turns unpredictable, the only option is to send teams down a pressurized vertical shaft. At depths of 40 to 60 meters, the air inside is kept at several times normal atmospheric pressure to keep seawater at bay. Every entry and exit becomes a calculated risk. Safety officers enforce strict decompression schedules, and workers spend up to 5 hours in staged pauses, dropping pressure in increments. eyes fixed on time charts pulled from the National Safety Code. Medical staff monitor every breath and pulse, ready to intervene at the first sign of decompression sickness. In these shafts, the margin for error narrows to minutes, and the line between rescue and disaster is measured in pressure gauges and protocol. More than 400 sensors are embedded throughout the tunnel's structure, streaming a constant flow of data, pressure, vibration, temperature, and humidity directly to control room dashboards. Every joint, every segment, every emergency exit is tracked in real time, with alerts for even the slightest deviation from baseline. These dashboards form a digital twin of the tunnel, allowing engineers to spot micro shifts in alignment or the first hint of water ingress before it becomes a threat. Emergency exits are spaced every 200 meters, and predictive analytics flag maintenance needs long before a fault can grow. With this network, the tunnel is not just built for today, but for a century of safe, uninterrupted operation beneath the sea. Engineering News Record called the tunnel a new bar for global practice, citing the precision and speed that trimmed nearly $14 million from projected overruns. At an American Society of Civil Engineers conference, a U.S. panelist described China's ability to field test and scale innovations as a wake-up call, noting that technologies still considered high-risk prototypes in the West were now proven at full scale. Western firms began updating technical codes and training modules, forced to confront a new standard in tunnel construction. Beneath the sea, China's tunnel now serves as a blueprint for future infrastructure rivalry. As nations race for engineering dominance, each breakthrough redraws the boundaries of what is possible and what is next.